scale gap. Yeah, there just isn't enough disk bandwidth to hold snapshots easily, and this would be a way out. What kind of APIs you would have here and so on, this would take some puzzling. Yeah, but it looks to me like a really interesting problem to think about. We talked quite a bit about network monitoring, diagnosis, and modeling. Michael will give a presentation about that, so I'm just going to skip that. One example that was, so we came back to the namespace of containers. Of course, the first thought everybody had, oh, we just put the containers in a file system, and with that we just took the monster out of the closet that we had just shoved into the closet. Yeah, so we decided let's not build a file system namespace for the containers, because then we're going back to where we didn't want to be. Yeah. So a flat namespace is perhaps a good solution. By the way, there is also something that we can learn here from systems like Amazon. Yeah, they have things like accounts and buckets and that sort of thing. So you could make it fairly organized so that people can still quickly see what kind of containers they have. The namespaces that should be visible inside containers, yeah, views, whatever you want to call it, that we listed a few examples, and POSIX of course did come up, because if you have some stupid old backup program or something like that, all it can do is just open and read and write files. So we still need something like that. Surprisingly, in 3 meetings that followed, nobody told me they needed a read-write version of this. Yeah, they all said, as long as my old backup applications can take the stuff off, I'm probably good.
When you say the different namespaces, would this be like one container and you have different views of the same data?
I'm afraid so, yes. Yeah, I think that a distributed container in some cases will need different views. But as far as we learned, primarily just for purposes like backup and that sort of thing. Yeah, not really for the application could do with its own view, and that was usually enough. Yeah, but the storage management tools brought another angle to it. People wanted a Hadoop namespace, by the way, whatever that exactly may mean. Yeah, they said if this system is well thought through, you could do big data modeling, so you could build a namespace. HDF5 got a lot of votes, by the way. There are all kinds of prefixes and postfixes, like it's now called XI-HDF5 something or something like that. It's no longer just HDF5, but I have refused to look up exactly what version we are at the moment. It's probably called HDF6 by now. By the way, an interesting question that came up was whether the system that we were discussing would actually be able to keep up with the exabyte per day example from the new telescope that was being raised. An exabyte per day is an interesting number. It's about a terabyte per second, I think. Yeah, so it's a little bit more even, I think. Yeah, they're 10 to the power 5 seconds per day, so it's roughly 10 terabytes per second. So it is really a phenomenal amount of intake from this thing. Yeah, frankly, it's going to be expensive to store that, and you would think that some form of initial data analytics would probably be a much better idea for that telescope. Yeah, so that there is sort of a dramatic reduction of the data before it is stored. I also don't really know, by the way, why. So the people who told us about this, they said you must be paying attention to reading data. I'm not really sure why they said that, because the intake is actually a write job, it's not a read job. Yeah, and I wasn't completely sure why this problem was labeled as reading, but these are not my words. I took them from the person who raised the requirement. So I think I want to move on to here are the pictures, but I'm sure that Michael will have better pictures. So we have a third meeting in Tokyo. This was also very interesting. So we went further here in defining. So what sort of things are in these distributed containers? What kind of APIs would one want to have, and we discussed that for a little while. Nikita's going to talk more about that, so I'm going to skip this slide. Yeah, but I just wanted to sort of show you how our thinking evolved. Perhaps the most interesting thing that was discussed in Tokyo was a case study. So we had a person from Tsukuba University, I think, talking to us about climate modeling, and he predicted, basically the weather or the climate for a very long time, and he raised some phenomenally simple problems. He said, everybody would like to know what is going to be the hottest day in Tokyo in every year, yeah, and actually extracting that sort of number from climate data was incredibly difficult. So their biggest problem was not to produce reasonable models, they said. Their biggest problem was to deal with that data afterwards, to index it. And so he mentioned two problems. One was the highest temperature. The other one was the lowest pressure, because they are very worried of typhoons. For typhoons, they kind of wanted to know, where is the lowest pressure, where are these typhoons moving, and that sort of thing. And the indexing of this data has become a massive problem, where database specialists don't know what to do with it anymore, and so on. There were all kinds of, in fact, the best solution was called, they said we need a database, and then they said the best database was called NoDB, which was sort of the opposite, because it was like an absolutely minimal infrastructure for indexing. What is very interesting is that some of the interfaces that we had defined earlier, I published this on a blog post actually somewhat before this meeting. We felt that the least we could do for these poor climate modelers was to offload and scale their problem. So we offered him some explanation of saying, we can, build these indices in such a way that at least, you don't bother your cluster with it. It runs asynchronously, and it can scale out to a whole indexing cluster that is sort of disjoint from the computational cluster. I think that made him moderately happy, but he wasn't convinced it was the final answer. The important lesson to learn is that people come up with problems that you really don't expect they come up with. They can sometimes be very simple, but involve a lot of data. We can't possibly in EIOW start solving all these problems, but we can hopefully give a framework in which people can solve the problems. Yeah, and so I think the emphasis that is very, very important is that we get that framework out of the door soon, because it started to turn out, and I'll come back to that in a minute, that almost the entire system consists of plugins to a framework. Yeah, little applications that build on the lower primitives, which is extremely attractive. Yeah, but without there being a prototype of the framework, it will be very difficult to try out if we're on the right road. Yeah, I'm pretty convinced we are, but we have to wait and see. So, by the way, a key concept in this data management system is that there is an operation log. So the operation log is useful for all kinds of purposes. First of all, for recovery itself. Yeah, you could replay your operations from an operation log. But you can also do things like incremental backups from it, yeah? Or you can be told there is a new file available. What I published on a blog post about was that you can do FSCK based on an operation log, yeah? If you know all the operations that have operated on the file system, you can extract them in an operation log and be ready to fix problems just by some random node scaling that problem out. This has to become usable through the stack. So Lustre, by the way, has an operation log, and people have built some application with that operation log, not so many, but it's a good starting point. So we came up with something that we call the file data manipulation language in Zyrotex, and then we changed language actually to interface, because it wasn't really a language, it was more of an interface. So that was very much based on the one hand, having the operation log, and then secondly, we had things that were called update streams, which are at the bottom here. So there are two problems one is quickly knowing what you need to do. So you want to look in an operation log, which files do I need to back up, for example, which files need to go to HSM. But an equally important problem is to know what have I already done. And so if, for example, I am replicating a file system, it is very, very important to know which is the last record that I have replicated. And at the moment, there are no interfaces to do that. Yeah. So if you create a file on a replica, there is usually no indication what is the origin of this file creation. Does it correspond to something in an operation log somewhere else? And so these transactional update streams are extremely important. And if you have these and the operation log together, you can actually solve an enormous amount of data management problems in a very systematic way. And so this is a good example of a framework that could be bolted onto Lustre very, very easily because the operation log exists, and an update stream is actually not particularly difficult to build because Lustre internally already tracks updates, at least on the servers, for its own recovery. Yeah, so it would be very easy to extend those facilities to a data management application. Yeah? So these were the sort of things that emerged in our 3 meetings. So I want to skip to the Barcelona meeting. So there's probably lots on these slides that's interesting, but they are on the web. So what we started to come up with in Barcelona was this picture for the whole EIOW system. And so very, very important is that we first of all mentioned that there would be a so-called storage interface that would go to something like an object store and a distributed database. And the objects stores are numerous. Yeah, I mean, Lustre is for HPC probably the most likely candidate, but the web community has built many others. The distributed database, I think, is a much bigger puzzle, but there are dozens of them. The reason that I think it's a much bigger puzzle is that they've never been used for storage applications, really. Yeah, nobody has built a file system with these things, and people have actually had very bad results building file systems with SQL databases and so on in the past. It's very easy to define a schema for a file system in a SQL database, but the performance is so rotten probably that it has never emerged as a contender in the actually used file systems. So I'm actually very keen to pin Eric Barton to the wall here later and ask him, so what database is going to do a good job? Because that, I think, is an important question, yeah, that we don't really know. The other APIs are the APIs I've talked about a lot. APIs for I/O, to define schemas or use schemas, doing data management, information lifecycle management in a way special case of data management. And so this is what you really would call application APIs, but they would also be used by tools and by a job scheduler. Yeah. So I think that this is what you would think as the user APIs for EIOW, and this is what the storage vendors will want to use for their backend here. So then we came to an initial division of various components in 3 groups. So the biggest group is what we have called the simulation and modeling part. And there was, by the way, in some other version of this picture, I used the word learning in here too. So this would take the operation log and analytics data, like how fast did the operations go and that sort of stuff, and feed it into visualization engines. By the way, remember that these kind of operations happen on perhaps dozens or hundreds of servers. So merely dealing with this information that comes out for monitoring and management purposes is quite an interesting task that other people would call a cloud problem, probably. Yeah, they would do data reduction techniques and so on. So we wanted to have a simulation engine and be able to always say, okay, we can visualize the real data, but we can also throw the real operations back in the simulator and visualize them again. You have to be very, very careful with simulations of storage systems. Some simulations have been very successful and some have been very poor. So if you don't start with checking that your baseline is good, I think you are going to lose. Yeah. So it's going to be really important to be able to compare reality with anything you simulate. But once you do that, you could have an operation log editor that basically says, okay, let me change all the buffer sizes, let me make the directories bigger or smaller, let me use different schema, throw it back in the simulation engine, and hopefully get a comparison with a modified system. That wasn't good enough, said some people. So they said, we want to be able to adapt, and so we want to take these logs and throw them in some kind of machine learning machine to influence, for example, how data would be stored. So if it is detected that a file is not widely striped, maybe, then the machine learning component could say, I will change it into a very widely striped file, and send messages through APIs, by the way, that are maybe no different from the ones here, and affect the system while it is running. We had more difficulties keeping these two things separate. There were certainly some things that belonged in the RAS component, like data collection and reduction. By the way, this is a problem with Lustre. I believe that the logging system that exists is seriously insufficient for what we want to do with it. Yeah, I think that this is a challenge. So the data collection and reduction is one element. Configuration management will obviously be a problem for a system like this. Just because this A actually means availability, we put it here, but availability is really something that could be seen as very much a core part of the system. So I'm not completely sure that availability doesn't belong here. On top of that, the so-called fast communication system for I/O and so on will probably be shared by the availability system. So I'm still not completely convinced we've got the right boxes here. Yeah, but it probably doesn't matter all that much. So in the interfaces component, we have schemas and containers. So internal format descriptions for files. Yeah, we need some kind of language to do that sort of thing. Tables, relationships, layout, performance, lifecycle management. Yeah, these are the key attributes that we have to address. And then we want to, of course, immediately have sample schemas. Yeah, if we don't come with sample schemas, nobody can use the system, and we would have something that will gather just dust. Then we have lots of interfaces, and we group them in collections. So there are interfaces for I/O, metadata, and transactions. There are interfaces for schemas, interfaces for resource management, and the FDMI interfaces, which I just discussed, the update streams and reading change logs and that sort of thing. And there's a very large list of sample FDMI plugins. So for example, hierarchical storage management, migration, all the lifecycle things, FSCK, searching and indexing, yeah, and these all become plugins that could be developed separately. And that is, of course, very much in line with the initial thinking that we build a language in which we can solve storage problems, yeah, rather than build a monolithic thing that solves them all in one blow. So in the good spirit of sticking to the schedule, I have gone 2 minutes over time, and I will stop right here. Yeah? And so this is roughly where the project is at today. The future agenda and so on, we should probably talk about at the end of this meeting at 4:30 or something. Thank you. So I don't know if the two of you